This is part 3 of the treatment of gas laws for AP Chemistry. Kinetic molecular theory of gases, which you may have studied in first year. Kinetic, of course, refers to the fact that gas molecules are constantly moving. The first point of kinetic molecular theory is that gas molecules can be considered to be geometric points possessing mass but no volume. That means that gases are always composed of molecules separated from each other by a big distance compared to the dimension of the molecule itself. Gas molecules, again, as we know, are in constant random motion. Moreover, if molecules collide with each other or with the walls of the container, those collisions are perfectly elastic. No energy is gained or lost. Gas molecules are considered to exert neither attractive nor repulsive forces on one another. The perfect gas will then go ahead and condense in terms of getting smaller and smaller in volume all the way down to absolute zero, but they won't condense in terms of turning into liquids. Now we know that all gases will turn into liquid at some low temperature. The average kinetic energy of the molecules is proportional to the temperature of the gas in kelvins. That means that any two gases at the same temperature will have the same average kinetic energy. Those are the four postulates of kinetic molecular theory, some subdivided. Now, let's talk about that with respect to what it means to our gas laws and observations. Imagine compressibility as an issue. All gases are compressible. Well, that really relates to the fact that the molecules are in constant random motion and very far apart from each other, which means you can push the gases closer together very easily. Well, not so easily if you get to very high pressures, but gases are all then compressible. Let's look at Boyle's law. The pressure on a gas or of a gas is going to be proportional to the collision rate with the wall where the pressure is being measured. And the collision rate is going to be proportional to the density of the moving molecules. We might call it the number density. The number density is going to be proportional to the reciprocal of the volume. As the volume gets smaller, the density gets larger. Therefore, the pressure must be proportional to the reciprocal of the volume. That's Boyle's law. Let's look at Charles and Emmentaon's law. The pressure is going to be proportional to the collision rate between the molecules in the wall. The collision rate is going to be proportional to the average kinetic energy of the gas molecules. As the speed goes up, the collision rate will go up. The average kinetic energy, of course, is measured by the temperature, by the absolute temperature, which means the pressure is proportional to the temperature. Likewise, the volume is proportional to the temperature by a similar argument. Kinetic theory of gases also helps us to understand Avogadro's law. The pressure is going to be proportional, as we said, to the collision rate between the moving molecules in the wall. The collision rate is going to be proportional to the moving molecule density. The moving molecule density is going to be proportional to the number of moles. Therefore, the pressure is proportional to the number of moles, as it says here. Dalton's law of partial pressures is explained similarly. If molecules do not attract or repel one another, then putting one molecule, one gas, together with another is not going to affect the pressure of either, which means the total pressure is going to be equal to the sum of the partial pressures. Dalton's law. Now let's move to a new question, and let's talk about the distribution of molecules of a gas. Over here we have a apparatus, an experimental apparatus, where a couple of wheels are turned by a motor. There's an oven here that discharges hot gas molecules through a collimator and does it in bursts, because this rotating chopper has a slit that only allows a small packet of these molecules, these gas molecules, through. On this side we have a detector, maybe something that is coated in such a way that it reveals the presence of the gas coming through. It is found that there is a distribution of molecules by speed. The fast molecules, of course, hit the plate first. The slow molecules hit the plate last. The distribution of speeds, this is just for nitrogen gas at 3 different temperatures. You can see at 100 Kelvin we have a distribution pattern here that tends to be kind of high in the low speeds. When we heat it up to 300 Kelvin, we get this spreading out here so that the average is much higher than in the first. And at the 700 Kelvin range, we have a very broad distribution with a large number of molecules on the high end. What that means, of course, is that this curve is depressed every time we heat up the gas molecules, because more molecules are going faster at higher temperatures. If you look here also, you can say that at this particular speed, only a tiny number of molecules are at that speed at 100 Kelvin, and at 300 Kelvin and at 700 Kelvin about the same amount are, because the 700, of course, has pushed over way to the right. Now, for 3 different gases at the same temperature, we find that this massive gas of chlorine, Cl2, 71 grams per mole, has a lower distribution at higher speeds and a higher distribution at the slower speeds. The average chlorine molecule moves in that manner. Nitrogen, being less massive, has a distribution that is a little bit skewed more to the right, and so it has more molecules at higher speeds. Helium, at 4 grams per mole, which would be the lightest element that we have on this chart, has a large number of fast molecules and a very small number of slow molecules compared to nitrogen and chlorine. This, of course, means that the diffusion of gases is going to be dependent on their mass, because the speed is dependent on their mass. So chlorine, very slow speeds; nitrogen, faster; helium, fastest. Now, it is found that the root mean square velocity for any given gas is the square root of 3 times the gas law constant times the absolute temperature divided by the molar mass. Gas diffusion is the gradual mixing of molecules of one gas with molecules of another, and it's taking advantage of the kinetic properties. Here you can see hydrochloric acid turning into hydrogen chloride gas, and ammonium hydroxide turning into ammonia gas. And it appears that the mixing and reaction of the two gases to form ammonium chloride is densest over here next to the hydrogen chloride, because the ammonia has a 17 mass, the hydrogen chloride has a 36 mass, and so which one is faster? Obviously the one with a lower molar mass. Ammonium chloride smoke is formed more towards the HCl bottle. The rate of diffusion or effusion of a gas is inversely proportional to the square root of the molecular or molar mass. Now, it's easy to forget this. It's easier to miss this. The rate of molecule 1's effusion or diffusion over the rate of molecule 2 is equal to the square root of the molar mass of 2 divided by the square root of the molar mass of 1. Alternately, you could just divide the molar masses and take the square root of the result. That's the same thing. So, the question is, what is the relative rate at which helium diffuses through a pinhole relative to methane, which is 4 times more massive? The molar mass of methane 16, the molar mass of helium 4. We do the math, and the rate of helium divided by the rate of methane is equal to the square root of the mass of methane divided by the square root of the mass of helium. Of course, this means we have 4 divided by 2, or 2. What that means is that helium, although it's 4 times less massive than methane, only diffuses twice as fast. And the reason for that, of course, is the definition we saw in a previous slide of the root mean square velocity of the molecules. Now let's talk about real versus ideal gases momentarily. No gas is ideal. What messes up the ideal nature of a gas? Well, molecules really can attract each other. We'll see that's van der Waals attraction, for instance, or there may even be a polar-polar attraction. Maybe some might even repel each other. So, kinetic molecular theory assumes that there is no attraction or repulsion. So what do real gases do? And, of course, what are real gases' molecular volumes? Well, 1 mole of ideal gas, we've got PV equals nRT. The number of moles in is PV over RT, and is 1. The trouble is, when we divide PV over RT, as you can see for ammonia, we do not have ideal behavior. It should be flat, nor for methane, nor for hydrogen. As the pressure increases, PV over RT, in this case, drops and then rises. In this case, just keeps on rising. So, we have attractive forces operating down here, and repulsive forces operating up here. How do we determine from structure whether we expect attraction or repulsion to rule? What is the most ideal gas here? Well, our assumption is that molecules have 0 volume. That's false. So we can correct for the volume of molecules, n times b, and we can put that now in the denominator. We have to subtract because the volume is actually less because of the small volume of the molecules themselves. B is the molar volume. Our assumption that the molecules have 0 attraction is false. So we're also going to reduce the pressure by a correction. And that's A, which is a constant for each gas, times n over v squared. A depends on the gas we're using. This leads to an equation called the van der Waals equation, which you will not have to use for your AP test. And this is the corrected pressure volume ideal gas law. The pressure plus the correction factor times the volume minus the correction factor divided by n is equal to RT. We correct the P, we correct the V. Now, think, if V gets very big compared to B, then it looks ideal.